Get ready to get fired up for thermochemistry because it's week 2 of Chemistry 14B. Hello chemistry community, welcome to EverWonder, the only show that cannot work on an original title card or be punctual with their uploading their videos because they got sick. Picking up from the last video, heat capacity is the energy required to raise the temperature of an object by 1 degree Celsius. Therefore, our equation is heat over the change of temperature. And as stressed before, if heat exchanges at a constant pressure, it is equivalent to enthalpy, so we get this bad boy. Heat capacity at constant pressure is equal to the change of enthalpy over the change in time. But what if we don't have constant pressure, rather constant volume? Well, by definition, heat exchange without constant pressure is just heat. But for heat capacity, we have heat capacity at constant volume is equal to the change of internal energy over the change in time. I'll discuss more about internal energy in a few minutes. Dividing heat capacity by mass will give us specific heat capacity, and if we use moles instead of mass, we get molar heat capacity. What makes specific versus molar heat capacities different is their extensive intensive properties. Properties that are independent of the amount of matter calculated are intensive, while properties that are dependent of the amount of matter calculated are extensive. Take a look at this chart. Heat capacity is rewritten to solve for heat alone, and as we know from the last video, we distinguish heat from temperature as the flow of energy, heat, due to a temperature gradient. Therefore, if there is no change in temperature, this equation cannot function. Okay, so how do we use this? Say we had a perfect system in which heat of the system plus heat of the surrounding equals 0. This is not accounting for friction, loss of energy, etc. That will basically mean that Q of the system is equal to negative Q of the surrounding, to account for no energy loss because heat given off by the system is also heat being absorbed by the surrounding. Take a look at this example. A 140 gram sample of water at 25 degrees Celsius is mixed with 100 grams of a certain metal at 100 degrees Celsius. After thermal equilibrium is established, the final temperature of the mixture is 29.6 degrees Celsius. What is the heat capacity of the metal, assuming it is a constant over the temperature range concerned? Well, for the water, they tell us it has a mass of 140 grams and its temperature is 25 degrees Celsius, while the certain metal they give us has a mass of 100 grams and a temperature of 100 degrees Celsius. Check and check! But what does this thermal equilibrium mean? They gave us a final temperature of 29.6 degrees Celsius, but that makes for 3 temperature values and we're solving for heat capacity of a metal. They didn't even give us the heat capacity of water. Well, what we do know is that we can use the specific heat capacity equation because we are working with mass, not moles, temperature and heat capacity, and we are given an example for heat capacity, #obvious. But we also know there are 2 different substances at play, water and metal. They are exchanging heat until thermal equilibrium is reached. Our big clue is thermal equilibrium because it tells us that these 2 substances will reach the same final temperature. Along that we have 2 different systems, we can account water to be the surrounding and the metal as the system, which gives us the following equation. Heat of the system plus heat of the surrounding equals 0, or more precisely, heat of the system is equal to negative heat of the surrounding. Since both equations are working with specific heat capacity, we can rewrite the equation as the following. Alright, things are looking a little cleaner. However, the question is asking for the specific heat capacity of the metal, so all we need to do is a little math to fix the equation up to have this. Bada bing bada boom, plug in our given information to solve. Yet, you may be a little baffled by the change in temperature, but it's rather simple. The temperature given for water and the metal are both initial temperatures because they will reach thermal equilibrium at 29.6 degrees Celsius, the final temperature. So to solve for the change in temperature, we just solve for the final temperature minus initial temperature being the temperature of the metal or water. On top of that, we also know water is a liquid because it is at room temperature at 25 degrees Celsius. The specific heat capacity of liquid water was not written in this problem because it is a constant, which is generally given to you on an equation constants chart. It is 4.184 joules per Celsius gram. As you work out the problem, you should get a little something like this. After punching into your calculator, you solve for the specific heat of the metal to be 0.38274 joules per Celsius gram. Of course, after doing some significant figures, your final answer should be the specific heat of 0.38 joules per Celsius gram. If you thought that was tough, wait until you crack into the real thermodynamics. First things first, definitions in these pretty charts. Thermodynamics is the study of transformation of energy from one form into another. Sounds familiar to thermochemistry? No? But you see here, we begin to distinguish what our system and our surroundings are. The system is the object of study while the surroundings is, well, whatever is not in the system, the region outside. Together they add up to make a universe. But consider the following systems. In this chart, we have open systems which can exchange both matter and energy. Examples include plants or car engines. Closed systems can only exchange energy, so such an example would be boiling water with a tight lid. The third system, isolated system, can neither exchange matter or heat. A bomb calorimeter is a commonly used example. Each system accounts for different ways energy is being added or removed. There are 3 ways to do so. One way would be to add or remove the amount of substance in a system, open systems of course. A second way would be heat or cool the system so only energy goes through. This can be done in open and closed systems. The third would be to do work on the system, compression, or have the system do work, expansion. This is only allowed for closed systems. You may be wondering, what is this work we're talking about? The formal definition for work is force being displaced over a distance, but for our purposes, work is performed on or by gases. We can rewrite our work equation by understanding that gases are compressionable, expandable. So using the pressure formula of force displaced over an area, we can rewrite force and substitute that into our work equation. Our grand work equation would be pressure times the change of volume. You're probably asking yourselves, where's the negative sign in front of pressure? Isn't work supposed to be equivalent to a negative value? The minus sign in front of the work equation indicates that a positive amount of energy done by the system leads to the energy being lost from the system. A pretty cool analogy a friend told me according to his PLF was that work is positive if a hairstylist works on your hair. It looks great on you if it's done on you. But should you style someone else's hair, it is negative because it will be worked out badly. That's of course not true for everybody watching this, but I thought it was pretty cool. If the pressure is equal to 0, that means that the gas molecules will naturally disperse to fit the volume of its container. There is no work, energy, that forces the molecules to stop or stay, thus freely expanding. With isobaric conditions, constant pressure, work can be solved for in 3 different ways. Pressure times the change of volume, and using the ideal gas law equation, pressure times volume is equal to nRT. The second form has change of moles, that is, the difference between of moles between the products and the reactants. The third form has change in temperature, which is pretty straightforward, finest minus initial temperature. With isothermal conditions, more precisely reversible isothermal, work is derived as the following within the chart. Do note that for the change in volume, it is final over initial, while for pressure, it is initial over final. If you're wondering why work done in isothermal conditions is all fancy and stuff, it's something more than a little calculus. Here's the math behind it in case you're interested how it is derived. Alright, so we know there are 2 ways to calculate for energy, as heat and work. Together they add up to make the total energy contained within a system. This is known as internal energy, delta U. It is a state property. This chart adds up from what we already know, but it organizes work, heat, and the internal energy all in one. And now give yourself a pat on the back because you already learned the first law of thermodynamics. Though formally, the first law of thermodynamics is an adaptation of the law of the conservation of energy, in which energy can be transferred from one form into another, but can never be created or destroyed. Internal energy of an isolated system is constant. That energy that is transferred is heat or work. And to finish off, let's look at some examples. Calculate work, heat, and the internal energy of 2 moles of an ideal gas at 295 Kelvin that isothermally and reversibly expands to twice its volume. We set up our internal energy equation. We also know that this is an isothermally reversible process, so delta U is equal to 0, and therefore heat is equal to negative work. We also know that there's an expansion, a change of volume, so our work equation will be the first one. We are given 2 moles of an ideal gas, the gas constant is equal to 8.314 joules Kelvin per mole, and our temperature is at 295 Kelvin. And as for volume, well, we actually know both the final and the initial volume. Say that the initial volume is x, the final one is just twice of that, so the final volume is 2x. But what do you know, we can simplify this down to 2. This could work for any ratio change in volume or pressure, just make sure that your algebra is brushed up to simplify these ratios. Alright, so now we have the following. And after solving this, you should get that work is equal to negative 3,400 joules or negative 3.4 kilojoules. Since heat is equal to negative work, that means that heat is equal to 3.4 kilojoules. And we're done in this one. And here's our final example. A piece of zinc metal of mass 50 grams at 150 degrees Celsius is placed in a vessel of negligible heat capacity, but containing 77.7 grams of water out of 25 degrees Celsius. Calculate the final temperature of the water. Assume that there is no energy loss to the surroundings. Our given heat capacities for zinc at 0.38 joules over Celsius grams. So here's a chart that has the given information organized. This example is a doozy because what we have here is a perfect system where no energy is lost. So we have heat of the system is equal to negative heat of the surrounding. Though not explicitly stated which is the system and which is the surroundings, we know that there is more mass of water than there is of metal. So the metal is submerged in the water. Therefore the water can be our surrounding, while our metal can be the system. So what we now have here is heat of zinc is equal to negative heat of water. And since we're working with heat capacities, this gives us the following equation. Now that we happen to know most of the information, we plug in what we know, giving us the following. We can then distribute that as, which simplifies to this, giving us a final temperature of 31.9 degrees Celsius. To take anything out of this video, I would think the charts, examples, and understanding of the phrasing of thermodynamic questions is pretty darn good. But hey, that's just week 2 of chemistry! Thanks for watching! Matt, that is so good at me when I stole his style.